So good morning to all. Today we are going to continue with the problem. Since the slide is scanned copy version, we can find during the video presentation the visibility is very low. So for that reason I have sent the copy of the same material. You keep that material. So keep that material. You keep that material so that you can able to follow the lecture. So this is problem number 6 of second chapter. So you download that particular thing and just keep with that. So I will explain with the reference to that particular paper. Okay. So it is already mailed to you. So yesterday it is mailed, as well as it is available in Google Classroom. So let me start the problem. So yes, it is a continuation of yesterday's problem. A solenoid is 50 centimeter long. So it is 50 centimeter long, 2 centimeter dia, and contains 1500 turns. A cylindrical core has diameter of 2 centimeter and a relative permittivity of 75. This coil is coaxial with second solenoid, also 50 centimeter long, but the diameter varies, which is 3 centimeter and 1200 turns. Calculate the inner and outer solenoid and mutual inductance. So here the diagram is given. Surely it is not visible. Diagram is given. So inner there is a one solenoid, outer there is a second solenoid. So 2 centimeter in dia and 3 centimeter in dia for the outer conductor. If I take in terms of radius 1 centimeter, 1.5 centimeter, the number of turns is 1500 turns, and here it is 1200 turns. So if I take the formula for inner, L inner is equal to mu n square A by L. If we substitute, this is the substitution, you will get L inner is equal to 132.2 millihenry. And if I take the outer, so outer contains both inner as well as outer. So this is inner and outer. So first inner formula is mu I n square ai by L, and outer is mu naught n square a naught by L. So if I take ai, I can find ai is equal to pi r square. Here r is equal to 1 centimeter. Therefore it is 0.01 square. So which happens to be some value. And a naught is equal to pi r square. I have to take this amount of r. So totally it is 1.5 and it is 1. If I minus 1 minus 1.5, it happens to be 0.015 square minus 0.01 square. So which is 3.93 into 10 to the power of minus 4. With all the known value, if I substitute, we will get the answer as outer is equal to 86 millihenry. And still the problem claims to find mutual inductance. So M is equal to mu naught mu r N1 N2A divided by L, which happens to be 106.6 millihenry. So second problem, a solenoid with 200 turns with 300 mm long and 20 mm in diameter. So we have to find L of the solenoid. If the current is 600 milliampere, find energy stored and density in center of the solenoid. And the second case is if the core is replaced by 500, here it is air core and here it is 500 mu r is used and a toroid is formed by bending iron core of solenoid with a circle. What will be the L inductance of it? So for finding the inductance, the solenoid, the formula is known mu naught n square A by L. Mu naught is 4 pi into 10 to the power of minus 7. N is given, so which is 2000 square into area. It is a circular cross section pi r square. So that is given here. Pi, this is pi value r square. So if during the calculation it happens to be 5.3 millihenry. Energy stored. We know energy stored is equal to, for inductance it is half Li square. So since it is half Li square, half 5.3 milli, which is calculated earlier, 600 into milli, which happens to be 9.4 into 10 to the power of minus 4 joules. And since energy stored is known, we can able to find the energy density, which is energy stored by volume. Volume can be replaced as area into length. Area, this is area, and the next one is the length. If I multiply the length, the answer is 10.05 joule per meter cube. Still, we have to find the inductance if I replace mu r. So this is the formula with all the known values. with the only change mu r is equal to 2000, I will get an answer, mu r is equal to 500, we will get an answer as 2.6 Henry. So that is a L for this second subdivision or third subdivision. Next one is a air core, which implies mu r is equal to 1. Toroid. A toroid concept is taken. The cross section is rectangular cross section with the turns of 700 turns with inner radius of 1 centimeter, outer radius of 2 centimeter, having an height of 1.5 centimeter. We have to find the inductance by using the square section formula and approximate formula. So for square section formula, the formula during the derivation under the subdivision of case, we know L is equal to mu naught n square h ln R2 by R1 by 2 pi. So if I substitute all the value, mu naught is known, n is known, h is given, R2 is given, R1 is given, 2 pi is constant, we'll get the answer as 1 millihenry. And if I want to use the approximate formula, which is nothing but L is equal to mu naught n square a by 2 pi r, first I have to find a. A is equal to height, this amount of height, average radius or radius of this system, R2 minus R1. So this is meter scale, it will become area 1.5, 2 minus 1, R2 is 2, R1 is 1, 2 minus 1 into 10 to the power of minus 2, 1.5 into 10 to the power of minus 4, and R is mean radius, one is 1 centimeter, the other one is 2 centimeter. If I take the average, it happens to be 1.5 centimeter. So R is known, area is known, and hence substitute all those value here and we will get 0.98. So if I want to take this formula, if I take this formula, it is 1.01. If I am using this formula, it is 0.98. There is no such a big change in the value. It is almost a nearest value. Next thing is we are finding the coaxial cable inductance. So for that, during the derivation, we understand L is equal to mu naught L by 2 pi ln B by A. So this is between inner and outer conductor. So B is given 7 mm, A is given which is about 1 mm given. So mu naught L length is 100 meter, 100. If I substitute, I will get roughly 39 Henry, micro Henry. That is the answer for inductance of coaxial cable. And the next problem is we are going to find the energy stored. A coil has a self inductance of 1 Henry. So 1 Henry is indicated and a resistance of 4 ohms. Resistance of 4 ohms is drawn here. If it is connected to a 40 volt DC supply, estimate the energy stored in the magnetic field when the current attains its final steady value. So with the help of the given data, if I draw a circuit which is having a self inductance and a 4 ohm resistance with 40 volt battery, a current is flowing here. So if I want to estimate the current is given by 40 by resistance. The resistance is 4, so 40 by 4 happens to be 10 ampere. So L is known, I is known, find energy stored. Energy stored is equal to 50 joules. So the answer is 50 joules of energy will be stored in such a circuit. So here the problem based on boundary condition. So in region 1, as shown in the figure, B1 is equal to given. Determine B2 and H2. So with help of boundary condition only, we can find if one parameter of B1 is given in one region, the other parameter in region 2 can be obtained. So it is a boundary based problem, B2, H2 in other medium. Also calculate the angle made. We have to find the angle, verify the angle with help of Snell's law, and also find tan alpha 1 by tan alpha 2. So here the diagram is given. Here it is region 1, region 2. In region 1, the medium is 1.5. In region 2, the medium is 1, air medium. So B1, H1, B2, H2, angle made is alpha 1, alpha 2. This is a given problem. So during our derivation of boundary condition, we have 4 important formula, out of which 2 is HT1 is equal to HT2 and BN1 is equal to BN2. With the help of this 2 formula, I can able to claim the other 2 formula. So first thing is H1. Here we are finding H1. H1 is equal to B1 by mu1. So B1 is given by mu1. So in medium 1 it is 1.5 mu naught. So therefore if we substitute this amount by mu naught from the figure, it is a normal component. the direction of normal component is z. So this is z axis, and therefore from the given data or from the h1, the value will contribute a normal component. So the normal component is hn1 is equal to this value. If h1 is known, hn1 is known, from h1 I can find ht1. The remaining component is nothing but ht1. So ht1 is written there. Also, from the basic law of boundary condition, hn1 by hn2 is equal to mu r2 by mu r1. Therefore, hn2, already we obtained h1, we have to find hn2 from hn1. So which is 1.5 by 1 into, that is hn2 is equal to this amount inverse into hn1. So if I do that, I'll get 0.4 AZ by mu naught. So knowing hn2, we have to find ht2. So with the help of the boundary condition itself, ht1 is equal to ht2. Therefore, straight away we know ht1, that is ht1, which can be written as ht2. So ht2 is known, hn2 is known, total h2 is equal to addition of these two. So that is given. So if I add those two value, I will get 0.8 ax, 0.5 ay, 0.4 az divided by mu naught ampere per meter. So knowing H2, we can find B2. B2 is equal to mu2 H2. So mu2 is nothing but, here the medium 2 is air medium. So simply mu naught, mu naught get cancelled. Remaining value, which is nothing but 0.8 AX plus 0.5 AY plus 0.4 A is the Tesla. That is the obtained value. So knowing, we obtain B2 as well as H2. So next thing is we have to find alpha 1 and alpha 2. Since from the figure I can write cos alpha 1 is equal to bn1 by b1. So bn1 is known, with help of modulus it is 0.4 square. b1 is three valid component, so square. If I do that, I will get some amount. If I take cos inverse of this particular amount, I will get 74.5 degree. Similarly, if I write cos alpha 2, bn2 by b2, we can write alpha 2 is equal to 67.4. So alpha 1 is obtained, alpha 2 is obtained. So since alpha 1 and alpha 2 are known, we can verify the Snell's law. So from the theory portion, the Snell's law is given by tan alpha 1 by tan alpha 2 is equal to mu r1 by mu r2. So since alpha 1, alpha 2 is known, we can find tan alpha 1 by tan alpha 2 is equal to 1.5. If I take the ratio of mu r1 by mu r2, that is also 1.5. So Snell's law is get verified, and hence it is verified. And one more question, tan alpha 1 by tan alpha 2, we already got that, it is nothing but 1.5. And this is a problem based on one boundary condition. Here, the boundary condition based on first medium is given, and we obtain the second medium. Whereas, still we can find the second medium may be given, we can find the first medium with the help of all the four boundary conditions. Next problem is also based on boundary condition. So a figure is given, it is a figure. So it is z axis, So therefore the normal component will be z. The remaining two components x and y will be a tangential. Medium 1 is 4, medium 2 permeability is 3. Alpha 1, alpha 2 is given, h1 and h2 is given. So here the same thing is defined here. A current sheet is given 9 AY. So if the current sheet is given, we should understand HT1 minus HT2 is equal to 0 as per the previous problem. But since the current sheet is given, HT1 minus HT2 is equal to a normalized vector cross the current sheet. So that is the formula. The only change is the formula will change here. With all those interpretation from the H1 given, I can write HN2 is equal to 8AX. The HN1 is equal to 14.5 AX. There is no Y component at all. So therefore HN1 by HN2 is equal to mu2 by mu1, and hence HN1 is equal to this amount into HN2. So 3 by 4 into 8 AZ, which happens to be 6 AZ. So we know that HT1 minus HT2 is equal to AN cap the cross K vector. So K vector is given, therefore AZ is equal to AZ cross 9AY. So therefore HT1 is equal to this amount, and HT1 is equal to 5.5 AX. So this is HT1. So HT1 is equal to 5.5 AX, and HN1 is equal to 6 AZ, and hence if I add this two value, I will get H1. I will get H1. The fan put in. I'll get H1. If I add this 2, I'll get H1. So that's all about your problem. So here we can able to understand that the light எல்லாம் போட்டுருங்களேன், எல்லாம் போட்டுருங்க, முடிச்சு போட்டுருங்க. கொஞ்சம் ஃபர்ஸ்ட் இருந்து திரும்புவாங்களே. கொஞ்சம் மேலே போங்க, மேலே போங்க, மேலே மேலே இந்த ப்ராப்ளம் பாருங்க. இருக்கட்டுமே, கொஞ்சம் லைட் இல்லாமல், இல்லை சார் லைட் இல்லாமல் என்ன தான் தெரியுது பார்ப்போம் கேமராவில் ரெக்கார்ட் ஆகும்போது. So here I think you can't able to visible, but still I will read out the problem. If you have the paper, you just refer the paper, that will be useful to you. An iron ring of permeability 100 is given, which is wounded with two coils, one is 100 and 400. Therefore there are two coils, one is 100, the second one is 400. The cross section is 4 centimeter square. The circumference 2 pi r is equal to 50 centimeter. We have to calculate self inductance, mutual inductance, total inductance. So in the case of total inductance, we have two things. One is when the coil are connected in series with the same sense. So we know that when there is an inductor, inductor will have current in, current out. When current in and current out are the first inductor, is similar to the second way, current in and current out, that is called same sense. It is the opposite way, it is called opposite sense. So during that we have to find the total inductance. First L1, we know that L1 is equal to, as per the usual formula for a toroid, it is a toroid problem, it is mu n1 square a by 2 pi r. Mu is 100 mu naught, n is 100 and area is equal to 4, 2 pi r is equal to 50 centimeter. With that we will get the answer as 1 millihenry. Similarly L2, with L2 number of turns is changed, with the change in turns I got the answer 16.08 millihenry. Therefore this is the first answer. Second, mutual inductance, M is equal to K by root L1 by L2. K, here in order to find the K value, I have to take the ratio of two things, R1 by R2. Since both are same, the ratio will remain same. It is equal to 1. K is equal to 1. L1 is obtained. L2 is obtained. Substitute, will get 4.02 millihenry. And therefore, for same sense, it is a same sense problem. It is L1 plus L2 plus 2M. If it is the same sense, it is plus. If it is the opposite sense, it will be minus. If I add all these parameters, the first problem, the same sense will be 25.15125 millihenry, and the second problem 9.045 millihenry. Okay, so these are some sets of problem. So in unit number 3, we solve lot of problem. Let me summarize those problem what we have seen. So the board எடுத்து கீழ வைக்கலாம் சார். up board கீழ வைக்கலாம். கீழ வைங்க. அந்த ஜன்னல் திறந்து விட்டுருங்களேன். திறந்து விட்டுருங்க. லைட் இருக்கு. ப்ரொஜெக்டர் ஆஃப் பண்ணிடுங்க. ப்ரொஜெக்டர் ஆஃப் பண்ணிடுங்க. So we have started unit number 4 with Biot-Savart law. That is the first thing. Unit number 3 is Biot-Savart law. So the important formula is dB is equal to IDL sin theta divided by 4 pi r square. This is the first formula we have used. Second thing is we applied H field for finite conductor. So for finite conductor, we have one important answer. H vector is equal to I divided by 4 pi r cos alpha 1 plus cos alpha 2 in the direction of A phi. I can write whenever the current is flowing in this direction, the flux will be rotating flux. Whenever the current is flowing in the circulating direction, then the flux will be normal. So that is a converse. It is a converse. If it is a infinite nature, suppose there is an infinite case. So for such a case, H vector is equal to I divided by 2 pi r the direction of A pi. This is a second set of problem we have solved. In a third set of problem, H vector for circular conductor. If I take a circular conductor, then I have two formula. The one is I or H vector. H vector is equal to I r square divided by 2 pi r square plus z square 2 r square plus z square power 3 by 2 is one formula. This is if I take a circular conductor, I am placing a point capital P. So if it is away, if I find the H here, this is a formula. Suppose if the P is dropped down to here, this point at the center, it is on the axis, and H vector on the center at the center is, if I put Z is equal to 0, I will get I divided by 2R is the answer. So that is a third set of problem we have solved. Next thing is we applied Ampere's law. In Ampere's law, integral H dot dl is equal to I enclosed. That is one problem we have solved using this. One more problem, flux is equal to double integral B vector dot ds. This is one problem we have solved. While taking that, we took B vector is equal to mu into H vector. That is one more condition. With all this condition, we applied those conditions under Ampere's circuit law, and we got the answer. Next thing is energy stored. In the energy stored, we did one problem. So here we took W is equal to half Li square. So that is a very important case, and therefore energy density is equal to the same amount divided by volume. So that is one set of problem we have solved. Next thing is we have solved the problem based on solenoid and toroid. So with that condition, we took L is equal to mu n square A divided by L for the case of solenoid, and L is equal to mu n square A by 2 pi R in the case of toroid. If it is a rectangular cross section, it is length into breadth. If it is circular cross section, it is pi r square. So that is the one we have solved. Next thing is we done based on boundary condition. With help of the boundary condition, we have four important formula. One is HT1 is equal to HT2 is a one formula. Second one is BN1 is equal to BN2 is a third formula. From here, I can write BT1 by mu1, let I put it the same way, mu1 is equal to BT2 divided by mu2. This is the third formula. And from here, I can write mu HN1 is equal to mu1 HN1 is equal to mu2 HN2. So these are the four sets of formula with help of boundary conditions, and therefore these are the formulas we have used to solve the 20 problems. We have did some 20 number of problems in this unit number 3, and still we have to do problems on unit number 4 in the next forthcoming classes. So in class 1, in the next class, we will complete a wave equation along with subcases of Maxwell's equation. So what is the Maxwell's equation in terms of free space? That we will substitute. The next thing is we will do, so this is class 1. In the next class, class number 1, we will do that. Next in class 2, we will do problems on unit 4. So within a class, we'll try to complete problems on unit number 4. And in a class 3 and 4, we will try to complete unit number 5, a chapter which is finite element method. That is our aim to complete. So before ending the session, let me revise the formula on unit number 4. In unit number 4, we have started with Maxwell's, that is Faraday's law. So induced EMF is equal to minus n d phi by dt. This is the first formula. Next, JC is equal to IC by A, which is equivalent to sigma E to E. This is the second formula. Next, JD, displacement current density JD is equal to ID divided by A, which is nothing but epsilon DE by dt. This is the third formula. And if I want to put a total current density, it is JC plus JD. Next thing is I is equal to double integral J dot ds. Next, Maxwell's equations. So you know that the following Maxwell's equation will contains. So first one is from Ampere's law, which is integral H dot dl is equal to integral sigma E plus epsilon dou E by dou T into ds, or del cross H vector is equal to JC plus JD, which can be given as sigma E plus dou D by dou T. This is first formula, Maxwell's equation first formula. Second formula, Faraday's law. So with help of Faraday's law, we can write integral E dot dl is equal to double integral dou B vector by dou T into ds, or del cross E vector is equal to minus dou B by dou T. This is your second formula. Next thing is third formula, double integral d dot ds vector is equal to triple integral rho v dv, or del dot d is equal to rho v. And the fourth formula is double integral b vector dot ds is equal to 0, or del dot b is equal to 0. So this is the Maxwell's formula, and after that we will do the important formula, p vector is equal to E cross H vector, and there will be some parameter called intrinsic impedance, which is E vector by H vector. If I want to find the average power, P average is equal to half EH. Sometimes H can be written as E by H happens to be E square by eta, or sometimes half E into H. E can be written as eta H square. These are the two set of formulas available in order to solve the power problem. And still we can write eta is equal to 125 ohms. So eta is nothing but intrinsic impedance, which is 120 ohms, 5 ohms. So with the help of this set of formulas, we will solve some another 15 problems in the next class. So thank you.